Okay, let's get started. Thank you very much for joining us today. I hope you're having a great time at Unite. I'm José Emilio Muñoz from the graphics and gaming team in ARM, and I'm here today with Đorđe Đurđević from Nordeus. As you know, ARM is the world-leading supplier of semiconductor IP, and we have been playing an active role in shaping the mobile gaming industry for what's been now more than 25 years. And we are here today to tell you more about our collaboration with Nordeus in optimizing their latest title, Spellsouls. First of all, Đorđe will tell you more about Nordeus and their game, going a bit into detailing how they optimize their game in terms of lighting and bloom. I will then jump into how we collaborated together to optimize it further to achieve 60 FPS in a sustainable fashion. And at the end, I will briefly mention our tools, which are free to use and hopefully, as you will see, are a great way to get started in optimizing. So with that, I'll leave you with Đorđe.
Thank you. So hello, everyone. My name is Đorđe. I work at Nordeus as a software engineer, specialized in computer graphics, sort of. Nordeus is an independent studio based in Belgrade, Serbia. We have about 160 people. Our game, Top 11, is the most successful mobile sports game in the world. We have about 180 million registered users. The game we are going to talk about here, Spellsouls, is in soft launch. Let me first show you a short trailer for the game. All right, so with this game, we wanted to achieve AAA quality. And by AAA quality, I don't mean huge budget. What I mean is best-in-class user experience. We want our game both to look great and to run smoothly. And to achieve that, we decided we have to achieve 60 frames per second. Since we want our game to be played by as many players as possible, we have to support a wide range of devices, all the way from Galaxy S3 to the newest flagship devices. And that means quite a big range of devices. We were unable to achieve 60 frames per second, our goal, on many devices, no matter what we did, no matter how much we reduced the quality of graphics, we simply could not run it at 60 frames per second. So we simply decided to abandon somehow that goal and to run at 60 frames per second only on high-end devices and the upper part of mid-end devices. The art direction for our game was realistic fantasy style. As you can see on this slide, we have battlegrounds that are gloomy and dark, but also we have quite bright battlegrounds. Also, we have several characters that have to be shown in these conditions. So we decided to go with PBR-like shading. By PBR-like, I mean simplified PBR. We simply could not achieve to do it with the GGX-style PBR shading, which is popular on PCs and consoles, simply because it is computationally too expensive for most of the targeted devices. What we did is that we used the normalized Blin-Phong model. And you can see here some of the materials we are using in the game. This normalized Blin-Phong showed to be very good for leather, for rock, for stone, for metallic, or for wooden materials. It doesn't appear to be good for plastic, but we don't have plastic in our game, so we didn't really care about that. The next thing I'm going to talk about are lights in our game. We want our players to feel like very powerful spellcasters. That is why our spells are the most important visual element in the game. And we want our spells to somehow interact with otherwise static environment. And to achieve that, we added dynamic lights specifically to spells. What we did is that we added point lights, and we used the standard Blindfong model. The computations are done per pixel, and we use only the specular part of the model because it showed the best results in our case. And we want many lights to be present simultaneously on screen, just because of the spells, as I previously said. So the idea was to use forward plus rendering, simplified version of forward plus rendering. Why? Well, because our light sources, as you can see on this slide, use a relatively small area of the screen. So forward plus seemed to be a good choice, and indeed it allowed us to have many light sources simultaneously on screen. But on the other hand, that approach didn't work on about half of the devices. And moreover, many devices were unable to sustain even a single light source. So this approach simply was not good enough for us. And nevertheless, we wanted to have as many light sources as possible. And this is where our partners from ARM jumped in and helped us. The artistic vision of the game required us to apply some bloom effect, and that is what I'm going to talk about now. So on this slide, you can see one battleground without this bloom effect applied. This battleground, this scene, has a very powerful, very strong light source. And with that light source, we wanted the metallic parts to pop out in some way. For example, these golden lines on the ground or the metallic armor of the units should somehow reflect that light. And on this slide, you can see an exaggerated version of what the artists wanted to achieve. So this is quite exaggerated. And this, side by side, you can see the same thing for visual comparison. Now, what we first did is we tried the standard post-process bloom effect. As you probably know, it's not very cheap. Actually, it's quite expensive on mobiles. But the reason why this didn't work is that we used LDR rendering in our game. LDR simply means that we are using a small range of intensities for the lighting. And thus, the reason why it didn't work is that when the bloom effect is applied, all, for example, white pixels will be affected by this bloom effect, regardless of the origin of their origin. For example, white cloth would be bloomed as well as a very strong specular reflection. And what we wanted is to have the bloom effect appear only where the strong reflections are. So the next thing we tried is to use HDR rendering, which should allow us to have distinguish between white that is coming from white cloth, for example, and white that is coming from strong specular reflection. We use this frame buffer format, but it turned out to be also expensive, and it also requires tone mapping in order to appear correctly on screen. And moreover, it doesn't support alpha, which is necessary for visual effects and the spells. So this approach didn't work. What we tried next is what we called multiple render target bloom. The idea is to have two separate render targets to render to them simultaneously. One would be the normal color buffer that you see on screen, and the other one would be a buffer that would capture only the strong specular reflections. And that buffer would be then used in the final bloom pass as the luminance input. So on this slide, you can see that we tried with two formats of texture for this secondary render target. We used RGB24, and we also tried with R8. This RGB24 showed better results. They looked more pleasant to the eye, more correct, so to say. But the problem is that it required quite significantly more bandwidth than the R8 approach. So we finally decided to go with R8. And it gave pretty good results. The artists were happy. They said it's okay, even if it is not real HDR rendering. It was good enough for them. But the engineers were not happy. And why? You can see the reason on this slide. You can see that for Galaxy S7, the drop in performance when using this post-processing is about 10%. For Galaxy S5, it's almost 30%. And it's even worse for less powerful devices. The good thing is that this MRT, multiple render target bloom approach, didn't cost much more. So it's a good thing. But the overall cost was too high. And we simply decided this was not the good approach. And again, this is where our partners for ARM jumped in and helped us. I will now ask Emilio to give you the details on how they did it.
Thank you very much, Đorđe. So first of all, I want to go take a step back and look at the big picture. So as you know, we want to hit 60 FPS, and that means rendering the whole scene plus the bloom at 60 milliseconds. So as Đorđe described, Nordeus already heavily optimized this bloom effect with their multiple render target approach. And this achieves a process that goes less than 3 milliseconds. So this is like 20% of our budget. Can we do any better? First of all, we have to realize that energy efficiency is intrinsically linked with performance. So we should not always strive for a high FPS. We should also consider that we keep the device running well for a sustainable amount of time. So as you see in this graph, as we run the game in several high-end devices for 30 minutes, in all the cases, the device will overheat because it can generate more energy that it can dissipate. And this will throttle and give poor user experience. So again, focus not only on FPS, but a sustainable FPS over time. In terms of bloom, which is the most expensive part of this rendering pipeline, we consider two approaches. First, we try to focus a bit more, trying to make this MRT bloom a bit more efficient. And then we also turn into exploring other alternative methods. In terms of the post-processing bloom, what we did was focus on the area that was taking the longest time, which is the blur step. As Đorđe described, they're using a Gaussian blur on the frame and then do the final composition. So we thought, can we maybe take a filter that is more efficient? And we have this paper from a colleague at ARM, and he describes what the dual filter. In dual filtering, we take the frame buffer and downscale it in steps, applying this blur factor at each step, and we then upscale it back up. And in this process, we achieve a smoother blur, which is, in most cases, much more efficient, up to 14 times more efficient. I will show you how it looks like now. This is, for reference, the scene with no bloom. And this is with Unity's post-processing. This is for reference. As Đorđe explained, this was not suitable for Nordeus, as we want to only bloom the areas that are metallic. And here we were also highlighting other white areas that were not metallic. This is their MRT Gaussian blur. And I'm going to switch back and forth between the Gaussian and the dual filtering. So you can see what I mean when I say that dual filtering is slightly smoother on the edges when it comes to the blur. Then we turned around and thought, maybe let's try something that doesn't involve post-processing at all. We refer to it as texture-based bloom. The idea here is avoid post-processing. What we do is we use a bloom map generated directly from the glossiness map, since what we want is to apply this effect to the metallic areas. And this is simply highlighting the areas where we want to make it brighter and highlight the bloom. This is generated completely offline. The artist can tweak it. And then what we do to further optimize it is that we save it in the alpha component of the already used glossiness map. So this way we achieve, with a single texture lookup, we get all the information that we need. Then in the fragment shader, what we do is we use this factor from the glossiness, from the bloom map, and also apply a calculation that takes into account the angle between the view vector and the light vector at the pixel. So this is to create the effect of making things brighter where we are directly looking at a reflection of the light source. This is how it looks like for reference, no bloom. And again, I'm going to be going back and forth. This works very well on the terrain. It's a static mesh, and it's very cheap, as I will show you now. To summarize all the options that we considered. So on the very left, we have the scene, the terrain with no bloom. And as you can see, the texture approach that I just described is almost free. The only thing we're adding is a couple of arithmetic operations in the shader. The next two are the post-processing approaches. And as you see, both Gaussian and dual filter makes no difference. It's simply not affordable on this case. Remember I said earlier that Duel was much more efficient, and in here you cannot see that difference because Nordeus already heavily optimized Gaussian. They downscaled the frame buffer and then applied Gaussian on that, whereas the dual filter goes all the way from 1080p to apply the effect that I showed you earlier. And finally, for completion, we also have the Unity's post-processing stack solution. Now, the texture-based bloom won't work on dynamic objects such as characters, since the light, if we just make the armor brighter, the light will not go outside the armor. It will stay. It will just make like the specular brighter, but it won't create this bloom effect. So, since we still want to avoid post-processing, what we do is we try to simulate it in another way by attaching a script to each character that generates this little plane with a texture that, again, the artist can tweak and can position in different areas of the character to create this illusion. So you see the plane, how it looks like in the editor on the bottom left, and then on the right, how it creates this light bleeding out of the shiny hammer in this case. And again, the performance results show that both this approach and the texture approaches are very cheap compared to the post-processing ones. So now, if we combine this texture-based bloom for the static objects and the plane approach for the dynamic ones, we achieve a bloom effect that takes less than 1 millisecond. So we can say, great, now we have bloom, we can call it a day. Or maybe not. Now, we have to remember, what is our goal? 60 FPS, which means rendering the whole scene and the bloom. So what's our budget? The answer is there is no budget. Or to begin with, our game was not optimized, so it was taking 28 milliseconds just to render the base scene. So in reality, our collaboration with Nordeus started by optimizing the game so we could afford adding all these effects like bloom. Just here to recap, always start by considering the whole picture. And for this, we at ARM offer optimization best practices. This is our guide available to developers. And I'm going to go through some of the points here. I'll start with a quote from Peter Drucker. Efficiency is doing things right. Effectiveness is doing the right things. Peter Drucker is an Austrian business management consultant. And this observation comes from when he was looking at how companies often obsess in micro-optimizing different steps of their process. And it is usually the most successful companies are those that are mature to take a step back and maybe reconsider, are we doing the right thing to begin with? So in graphics, let's see how this could apply. How can we make sure that we're doing the right things to start with before we get too lost into optimization? Things like algorithm suitability. Are we doing the right things both in the CPU and the GPU? For instance, are we batching? Are we calling things on the CPU before we send them to the GPU? These are standard questions that we should always start with. And the most important one, avoid redundant work. This is avoid doing things that have no visual impact at all in the scene. Things like cooling, not drawing things that are outside the camera, things that are behind a wall. And this is the most important one because in here you don't have to trade off quality for performance. As that has no effect on the scene. And this is related to issuing only the calls that we need. And finally, issuing things in the right order. This is not so important in latest GPUs, but again, if we want to target a wide range of devices, we want to make sure we are doing front-to-back rendering to avoid overdraw. In terms of optimizations, in being efficient, we can maybe start by optimizing render state. Go draw call by draw call, make sure that you are setting it right. If my object is opaque, disable blending, enable backface culling. And again, if you have something that is not contributing much to the scene, like you have a mesh that is very far away, maybe you can simplify the meshes, you can throw it away altogether, or you can play with different levels of detail. And in terms of fragment shading, optimized textures, we have compression. ASTC can help you compress and save bandwidth both in color and normals. Meme mapping, very important. It will save you also, it will improve quality, which is, there's no reason not to use it. And only at the end, maybe we can think about optimizing shaders, because as you know, this is one of the most difficult things. It often requires expertise in performance analysis, and it doesn't always bring as much improvement as all of the other things that I mentioned and are easier to tackle first. So back to Spellsouls, we did an initial triage, and we found that the game was GPU bound. So if I show you this scene, which one would you guess is the area we should start optimizing first? The explosion? The character shaders? Explosion again? Well, the answer is don't guess. Profile it, use tools, make sure you know what you're focusing your efforts on, because it's easy to get carried away and make guesses and maybe not get as much benefit as you thought you would. So in our case, maybe counterintuitively, the most expensive rendering part was the terrain, because as you see, it's taking a very big percentage of the screen. And this is what we started optimizing. We looked at different things, and we started saving 1.2 milliseconds simply by switching to world space normal maps in the terrain. And in terms of reflections, we had some room for optimization, but we decided to leave that alone. Nordeus had some very crisp reflections, and we had instead more room in lighting, where we had 6.1 milliseconds that we could improve on. So we focused on that. And for that, what we did first was reduce the resolution of the Lightmap. This way, we are saving a lot of pixels every time we process each of the lights. And this also has a side effect that it will help us add more lights, because the more lights we add, they have a smaller contribution. And this way, we saved from 14.3 milliseconds to 10 milliseconds. And for comparison, I show you here the full resolution Lightmap being applied to the terrain. And this is the lower resolution. I'll go back and forth. And as you see, the effect's barely noticeable, whereas the performance savings are there. And as I said, adding extra lights is also very cheap this way, if you use a lower resolution light map. This gets us a bit closer to our goal, but there's still some room. And then we had to maybe look at other things, like reducing also the resolution of the color texture. And this way, again, we save the processing of a lot of pixels. And in this case, also go down from 10 milliseconds to 5 milliseconds. As you will see, it has a tiny effect on the visuals. Ignore the fog at the bottom. That was added later as well. But in terms of maybe the sharpness of the objects. But again, in the game, the camera will be focused in the center, and there will be characters and spells all over the place. So the terrain won't have the attention of the player, and the savings in performance are more than justified. And now, yes, we can say our game is rendering at 60 FPS and in a sustainable fashion. So here is our side-to-side, which you will have seen if you came by our booth in the expo area. On the left, we have the initial prototype of the scene. It was running between 30 and 40 FPS. And on the right, there is the one with Bloom, which is running at 60. Focus on the characters' armors, where the plane is being drawn, and the metallic ribbons around the scene.
If I may just say, in the upper left corner, you see the actual frames per second. It should be the current time of the battle, but we tweaked it just for this, to capture these videos.
So to finish, I just wanted to also mention our tools. These are available for free. And they consist of, first of all, on the right is Streamline. This is our system profiler. With this, what we do is a quick triage at the beginning of our performance analysis. We use it to focus, we see all the CPU activity and the GPU activity. In our GPUs, we expose a lot of hardware counters that this application will help you trace in real time. And also, you can use it to have an eye on memory usage. You can isolate your process. So in Android, you can ignore all other processes running on your device and focus only on your game. And then once you find the area that you want to focus on, you can move on to our Mali graphics debugger in the center. This is an API debugger compatible with OpenGL and Vulkan and GLES for embedded. And in here, you can. It's more of a. It's not a performance analysis tool because the interception of all these draw calls affects timing. But you can use it to visually inspect what you are telling the GPU to do and what the GPU is actually doing. You can. It also incorporates our Mali offline compiler, so it will compile all the shaders and tell you which are the shaders that are the most used. It will tell you in which fragments they're being used, and also how many cycles are going to load store, arithmetic, or texture. So to recap, use tools, always profile first. Make sure you optimize your efforts when you are optimizing your game. That means being effective as well as efficient. And always be open to explore alternative ways, as we did with Bloom, and find all these kind of optimizations. And let us help you as well. We are offering several tutorials and use cases like this at our website. We also have SDKs and sample code that you are free to try. And we're also quite responsive at developer@arm.com. And with that, I want to thank you very much for joining us. Any questions?
Sorry. You wanted this slide to appear?
Yes,
yeah,
fine.
okay.
What was the lowest device that you support 60 FPS on?
Oh. Actually, I don't know to answer that question. I think it's an S6, but don't get me. I would have to check. I don't know to tell you exactly.
Thanks.
If you come by our booth in the expo, we also have more people involved in the project, and we might, if you have any questions, we're also happy to guide you through our tools and give you a quick demo. Question?
I have a question. How did you do the shadows? Did you use the Unity's real-time shadows, or?
No, we generated our own shadows using shadow maps. We blended them with the Lightmap also, so we have some custom shadows.
Right.
Okay, hi. Can you explain why you use multiple render targets to store bloom value? Because you can use alpha channel and it will be faster. So you can use separable alpha blend to prevent your alpha channel to destroy it.
Some visual effects required that the destination buffer also that alpha value be used for visual effects. So we could not actually use the alpha of the destination buffer.
Okay, thanks.
Hi, thank you. Excuse my ignorance, but the ARM company, basically, you guys hired them to help you improve performance. Is this the collaboration?
Yeah.
So this is a service that you guys provide at ARM?
Yes, from time to time, it's in our interest to promote these tools and this best practice to all developers. So if you come by our booth, we can give you our contact, and we're always open to this kind of collaboration because it gives us an insight into the industry and hopefully also something useful to share with the community.
Perfect, thank you.
Yep, thank you.
All right, thank you.